In this video, we'll be looking at Chapter 15, Section C on vector addition. Now, we've already been working with vectors and we just didn't realize it. In Chapter 10, when we were dealing with bearing problems, we were really working with displacements. Now think of displacement as a vector because it has both magnitude and direction, and it's really just a distance traveled with a direction. So in Chapter 10, we may have seen a problem where a person walks 3 kilometers to the north and then 2 kilometers to the west, and we wanted to know what the angle or the bearing from, we'll call this point A to point B was, and we'll call that theta. Theta is our bearing. And if this is 3 kilometers and this is 2 kilometers, we can then calculate the distance from A to B. And so if I have both the distance and the direction, I really have a vector. Now let's suppose we have 3 towns, A, B, and C. Now if I want to travel from town A to town B, I can draw this displacement vector. And then if I want to travel from town B to town C, I can draw this displacement vector. Well, I can draw another vector directly from A to C, and this is really the sum of traveling from A to B and from B to C, in terms of displacement anyways. So I can write a vector equation here stating that vector AB plus vector BC is equal to vector AC, and this is vector addition. So there are 3 simple steps to add 2 vectors together geometrically, and what I mean by that is really by drawing them to scale, either on graph paper or with a protractor and a ruler. So there are 3 simple steps for adding 2 vectors together. The first step is to draw vector A. The second step is to start drawing vector B at the arrowhead end of vector A. So if this is vector A, that's step 1. Step 2 is to draw vector B at the arrowhead end of vector A. And the last step is to draw the vector A plus B, starting at the beginning of vector A and going to the arrowhead end of vector B. And that looks like this. So we call this A plus B. Now that we know about vector addition, we can really define the zero vector. And often in your book you'll see that 0 is bolded. That means that it's the zero vector. I can't bold my 0, so I have to draw an arrow on top to represent it as a vector. But a zero vector is like the regular integer 0. If I add 2 vectors together, vector A and vector 0, I'm going to get right back to vector A. Likewise, if I add vector A to its negative, I am going to get the 0 vector. Now remember, a 0 vector is a vector that has a length of 0 and doesn't really have a direction. Okay, let's look at an example problem. In this problem, we're given a polygon labeled A, B, C, D, E, and we're asked to find 3 vector sums. The first one I'll do in red, and we're asked to find vector AB plus BE. And so really there's several ways I can do these problems, but I can draw a vector on top of the line segment AB, and then I can add the new vector, which is BE, by drawing that vector at the tip of the first, and then remember my resultant is a third vector that starts at A and ends at E. So my vector here is really AE, or the sum. Okay, the next one I'll do in green, and we have vector DC, and then we go from C to A, and then we go from A to E. And so again, I'm going to start at D and end at E. So this vector is vector DE. Okay, and the last one I'll do in purple. I'm going to start at CB. I'm going to start at C and go to B, and then from B to D, and then from D back to C. So I start and I end at the same point. This means my displacement's really zero. I haven't really gone anywhere, or I came right back to where I started. So this is an example of the zero vector. If you're ever doing vector addition and you get down to a vector like DD, where it's the same 2 points, this is really the zero vector. Let's take a look at another example problem. Here we have Jason, who walks for 3.8 kilometers in the direction of 110 degrees and then 2.7 kilometers in the direction of 20 degrees. And we're asked to find his displacement from the starting position. Now there's a couple things that we need to take into consideration here. One is that we're dealing with bearings again. And with bearings, remember that 0 degrees is pointing north. Secondly, we're asked to find his displacement, which means that we're actually finding his direction and the distance traveled. And that's because displacement is an example of a vector. So whenever we're asked to find a vector, we need to find both the direction and the distance, even if it's not explicitly stated. So let's get started. We're going to start at his starting position, and Jason's going to walk 110 degrees, which is in this direction, and he's going to walk in that direction for 3.8 kilometers, and then he's going to turn, and he's going to walk 20 in a direction of 20 degrees for 2.7 kilometers. And we're asked to find his displacement, which is really the vector sum here. So I have a triangle, and I can figure a few things out about the geometry of this triangle. First of all, we know that this is 20 degrees right here below the east line, because the bearing, the original bearing, was 110, and that makes this 70 degrees. We're also given that this bearing is 20 degrees, so very conveniently here we have a right triangle, which means that I can find the distance of his displacement very quickly using Pythagorean theorem, and that looks like this. Okay, we square both legs of the right triangle, take the square root, and we get his distance traveled of his displacement is 4.66 kilometers. Now to find his direction, we need to find this bearing right here. And let's not call that theta, we'll call this guy theta. Now if we knew theta here, the inner angle of this triangle, I could subtract 20 to find this smaller angle in here, and then I could find the complementary angle, and that would be my bearing. So I'm going to use inverse tangent here to find theta, right? And inverse tangent is opposite over adjacent, so I'm going to take the inverse tangent of 2.7 over 3.8, and that's going to get me theta. And so theta is approximately 35.4 degrees. Well, if I subtract 35.4 degrees from the original bearing, which was 110, I get my final bearing of 74.6. And so really I have two parts to the answer here. I have the distance traveled and the bearing, and that's really important.